about different ways we can apply knots to different STEM fields. It's something that I'm really passionate about, and I think we're going to have a lot of fun today. So I do have the chat box open on my screen, so feel free just to pop questions in when you have them. I'll try to check that periodically. And this is just going to be kind of a lax day, so as you have comments or questions or things like that, just let them fly. What I want to start with is I just want to let you know a little bit about myself. So, and how I cope with COVID. So the first thing is, which you might get to see a little bit today, I am a fur mom. I have 5 pets, 3 cats and 2 dogs. So this is my family. We spend a lot of time outside and a lot of time on Zoom together. So these guys are my world. And this is really how COVID has, I've coped with COVID is with them. A little bit more about me. I tend to like darker things. I like board games that have a eldritch horror kind of feel or a murder mystery kind of feel. I love to read. Again, we deal into the little darker things. And I'm also a documentary kind of nerd. I like to learn. I like to learn all different things. So for $6, you can get a year subscription to Curiosity Stream, which is just documentaries. So it's like the best part of Netflix all at once. So that's how I spend most of my time when I'm not working. But today we're going to talk about knots. So what I do when I work. So I want to talk about the basics of knot theory, how we can look at it in other areas. And then I want to talk about active research combining these two things and what I do with my undergrad. So it was mentioned you have a colloquium, honors colloquium type thing going on, talking about research projects. So I'm going to talk to you what my students and I do together as well. So with mathematics, there are always different levels to things. So you can always add another layer of complexity. So I'm going to do that with the definition of the knot. So for knot theory, if you haven't taken Dr. Bozeman's classes, right? I want you to think of taking your shoelace, tangling it up, and then fusing the ends together so you can't untie it. So like with this headphone, which is kind of now an out of date example, right? Because we all have wireless earbuds. If I took the earbud here and the end wire and I fused them together, that would be a mathematical knot. Okay. We're going to talk about what it means to not have the ends fused together a little later. The definition I consistently use is that a knot is a simple closed curve. So simple means there's no self intersections, so you can't cross through itself. Closed means there's no end points, so the ends are fused together. Curve, and I'm going to put it in 3 space. So I want it to be a 3-dimensional object. Well, I want it to sit inside of 3 dimensions. So here is an example. This is the figure 8 knot. So this is called the knot projection. I'm just flopping it into 2 space. So the little gaps that you see, these aren't end points. They're just saying which strand goes over the other one. We're going to talk about this knot a lot today. This is the 4-1 knot. You can get a trefoil knot, which is called the 3-1 knot. And then here you can get the unknot is just a plain circle. So if you're tying your shoe, right, you go, you loop it together, and before you do the bunny ears, if you fuse the ends together, that would actually be the trefoil knot if you tie your shoes correctly. But there's one more definition of knot I want to go over, and that's the more technical definition. So a knot is really an embedding. It's a function, it's a map, right? You're going to take a circle, so I'm going to call my function K, and I'm going to throw it into 3 space, which I'm going to actually call S3, just a 3-dimensional sphere. So let's up it a dimension. But if you really wanted to think of it, you can think of R3. You can parameterize knots if you take in Calc 3, which is always kind of a fun task. And then you manipulate that in software a lot too. But for us, we're really going to just kind of focus on this definition. If you don't like these words here, just always think of that intuitive definition. That's the definition I give my family. So as a knot theorist, okay, so let's talk about the theoretical sense for just before we get into all the cool stuff. So the fundamental question of knot theory is, suppose I give you two knots, are they the same or different? Right, so think of Christmas tree lights or a string of lights, right? You put them away, they get all tangled up. You know, in theory, you should be able to stretch it out without any tangles, right? So they're technically the same, but how do you do that? How do you unravel it? So I want you all to look at this example. And these two are the same knot. So if you get bored during this talk and you have to stay on, try to figure out how you can get from the left to the right or vice versa. So it is possible to do that. And I'll do a quick example down below here. So two knots are the same if I can move one into the other position. So technically, we're going to use something called Reitemeister moves. Here, we're not going to do that. I'm just going to draw some pictures. So I'm going to start with our beautiful 3-1 knot. I'm just going to spin it a little, and I'm going to take this portion, and I'm just going to elongate it on the side here. So I'm just stretching it out. So now instead of having a set length of string, I'm looking a little bit more abstractly. We can move things and shrink things. And then what I'm going to do is I'm going to take this piece that I just played with, and I'm going to just kind of flip it over onto the other side and slide it over. I'm really secretly doing a lot of little things in there, but we can just move it over. And then I'm just going to take these ends and smooth them out a little bit nicer to look like that. So those are the same knot, they just look different. These are just different projections, we say, of the knot. Okay. So let me tell you about my family. So my family, what do they think of this, right? So this is leading into why I look at applications. So what does my family think I do? One, they think I untangle jewelry all day. So like I'm the person at family reunions that's like, hey, can you untangle my necklace? This is like what you do, right? So I get that a lot. I get that I know how to tie knots. I can tie my shoe, like that's about it. I don't know how to sail. I can't do that. My family thinks I can. At my wedding, we literally tied the knot as part of our wedding thing. So they're like, oh, so this is what you do. Like people actually thought that's what I did all day. So as a scientist, as a mathematician, you always need to be able to give a 90-second spiel about what you do to a variety of people. So I could tell you in the next, minute, what do I do? Well, I study a 4-dimensional invariant and I look at concordance and I do all these things, and that would mean nothing to you, right? I could say, hey, I study knot theory. It's like how we tangle like strings of lights. Like that's not accurate. So what I started to do with my family was give them the spiel. I'm like, oh, hey, DNA is knotted, so we can like tell more about the DNA structure if we know about knots. And like, that was like the one throwaway line. They're like, oh, okay, so you do real things, is like, and then they left me alone. Unfortunately, my sister is a biologist, right? And she immediately is like, that's BS. Like, what do you actually do? So, and then I thought about it for a really long time, and I'm like, I know knot theory is used to study DNA, but I don't know how. So that's when I took it upon myself to start learning more about these things. And that's what I want to share with you today, kind of a shallow dive into different areas of how we can apply this theoretical concept to more applicable campaign today, right? We're going to investigate how we can use a theoretical idea and apply it to more tangible idea. So I have 3 topics in this presentation. I don't know if we're going to get to every single one of them or not. We'll do our best. So I want to talk about molecular chirality. I want to talk about protein folding, and I want to talk about DNA site recombination events. So I do want to mention that this will probably be, we're going to do it last because it's the easiest to find material on. It's been around a little bit, the longest in terms of knot theory relationships. So I put down a couple of things here. So for our molecular chirality, so for our chemistry unit, we're going to talk about symmetry, and the knot concept we're going to talk about is going to be amphichiral knots. And we're going to talk about conditional statements. So if P implies Q, then not Q implies not P, things like that. Protein folding, this is my favorite. This is where my active research is with my undergrads. So I'm going to give you the actual problem that we're trying to solve with that. And this is going to talk about something called virtual knots. Anthony, do you talk about virtual knots in your class at all?
I do not.
Awesome. And we're also going to talk about knot polynomials. So given a knot, I can change it into a polynomial. So we're going to talk a little bit how to do that, but I don't want to keep it pretty light on the technical, the technical aspects. And then the recombination events, we're going to look at rational tangles. And I'm going to mention a higher order invariance. So we're going to, maybe given time, talk about two branch covers, but I don't think we're going to, but there's a higher level there. Now, I have to be completely honest. The knot pun's strong with this crowd. I like it. I am a mathematician first and foremost. I am not a biologist. I am not a chemist. I'm not a biochemist. I try to know as much as I can in relation to what I need. So if you want to know exactly how these bonds are working, what type of bonds in the molecules I have, I'm not going to precisely be able to answer all those little nitty-gritty details, but I'll do my best. I'll do my best. So let's talk about knotted molecules. So we can talk about knotted molecules in two different ways. We can talk about naturally occurring knots and synthesized knots. So naturally occurring, we'll talk about in our different protein folding and DNA recombo events. DNA can be knotted, proteins can be knotted. It happens naturally, or you can synthesize a molecule to have a knotted structure. So the molecule here on the right, I believe this is the 817 knot. And this one, the first time I taught my course, this came out a month before, so that was 2017, which is now already 4 years ago, which blows my mind. This was discovered in 2017. It was the tightest known knot that was able to be synthesized, so it gave a lot of a structure to that. Since then, there's been several more molecules of higher crossings that have been synthesized. Of note would be in 2000, I think it's 19, we had a 3-component link. I think that looked like this was like the rave in the knotted molecule scene. So this is actively something, people are trying to do, is synthesize knotted molecules. Of course, we have molecules that aren't knotted, as the bottom here implies. So just really quickly, dotted lines mean it's shooting out in the back of the page. Solid, thick lines means it's coming forward. So we're going to look at all those things. All right. So let's talk about chirality. So I could talk about, hey, molecules are knotted. Let's do some knot theory on those. But instead, I want to talk about the chirality of a molecule and talk about the different topological methods we'll do with that. So here's the basic idea. So I apologize. The idea of chirality and achirality. So suppose you have your left hand. That's not how a left hand looks. Sure. I'm married, so I'll put a little ring on my finger. Right. And I want to look at the mirror image of this. So I'm going to have a mirror over here. And then I'm just going to draw the reflection in the mirror. Okay. So note, this is the front of my hand. And in the mirror image, this is also going to be the front of my hand when I look at it in the mirror. Okay. If you can take an object and look at its mirror image and superimpose it onto itself, it's called chiral. Or if you can't do that, excuse me, it's called chiral. So think of it. Can you make your left hand into your right hand? Well, no, we can't, right? The best we can do is if we decide to spin our hand around. See, it's no good. My hand's morphing. Right. Then this one kind of looks like this one, except that this is now the back of the hand. And the back of your hand is definitely not the same as the front of your hand. So if you can take one side and superimpose it onto the mirror image and they're the exact same, you're called achiral. And this gets tricky, right? Because usually when we put an A in front of something, it means the opposite. Well, not in this case, it means the same. So an object is chiral if, oops, excuse me, it is not the same as the mirror image. A in front of something same when we usually don't. Just a little brief history, the Greek word chi. And Lord Kelvin, if you take a knot theory, you probably know Lord Kelvin, coined this for knots as well. So chiral means you have handedness. You can tell the difference between your left hand and right hand. Achiral means you're not handed, so you couldn't tell the difference between two. It's a little strange, but it is what it is. So why should we care? So let's look at some, there we go, some examples. So here I have the carbon molecule and I have the limonene molecule. So the molecules here, these ones have to do with smell. So depending on which molecule in the mirror image you're looking at, you have different smells. So if we're looking at this configuration of the molecule, it'll smell like, and if looking at the mirror, it'll smell like caraway, which is the vast difference there. And similar to the other ones, one smells like oranges, one smells like lemons. Okay, that's kind of cool. Like, okay, so you flip it, like mirror images of these molecules make you smell different things. That's kind of fun. Like, does that really matter? Well, it actually does, right? The chirality of a molecule is very, very important. So the one I want to talk about is thalidomide. So this was a drug given to pregnant women in the 1960s. I can't remember if one configuration of the molecule helped fight with nausea. The other caused a lot of severe birth defects, missing limbs, multiple appendages, things like that. So pharmaceutical companies are very interested if a chemical is the same as its mirror image, if a molecule is the same as its mirror image. It's very, very important. For instance, IB case, one has no side effects. So pharma companies can make both and send them off and it's fine. If you look at, I think Dravon's like cough medicine. And if you flip the other one around, it's a pain reliever. So that doesn't really make a difference. Other ones you might know, Noxaprin, one's toxic to the liver, the other one's some kind of pain reliever or something. So pharmaceutical companies really care about chirality of molecules. So this is an important topic, which will bring it back to knots now. So an amphichiral knot, and I put on the bottom here, it depends on your source, the chemistry book you're using, the knot theory book you're using. Really, any spelling of the word achiral or amphichiral is the same. So I'm going to draw the figure 8 knot. And then I'm going to put it in my mirror. And then I'm going to try to draw it. I'm going to try to draw it correctly. So there's my mirror image. I want you to notice, if you look at the crossings, they are exactly the opposite. So here, the left strand goes over the right. Here, the right strand goes over the left. So the mirror image of the knot, you just changed the crossings. So I don't have to draw this mirror anymore because we all see how well that goes, right? So if I drew the trefoil knot and I wanted to draw the mirror image of it, I would just draw it. So I would try to just draw it. So all the crossings were the opposite. So that's how we'll look at the mirror image for knots. So let's get into our chiralities. Awesome. Okay. So there's 3 types of chiralities we want to look with. I'm going to look at knots and I'm going to look at molecules. So an object is geometrically chiral if there is no rigid motion that takes it to its mirror image. So we're talking rotations, we're talking translations, we're talking some reflections. We got to be a little careful there. So let's look at this example. So I have a knot. I know its mirror image is just all the crossings changed. So I just changed all the crossings. If you want to see how to go from this one to this one using a mirror, you got to find out where to place your mirror. So that's a fun little thing. But this is geometrically chiral because if I take another one of it and just rotate it, I see that I get the one on the left. So if we just rotate, and a rotation is a rigid motion, even though I'm like zooming out on the picture, it preserves distance, right? So this is going to be geometrically achiral because it's the same as its mirror image. And this is also that 4-1 knot we saw before. All right. So then we have some chemical and this one is going to be chiral. Now the problem here a little bit, it's a little hard to see because they're not 3 objects, but one we're just going to, this atom stays in front, this one goes behind, and this one parallel to the screen. So these are going to be the same. These aren't going to be the same because I really just want to take those 2 and flip them. So I can't just move 2 things in my molecule. I have to move the whole thing. This one's fun. We don't really care. We care about this one. Is it chemically chiral or achiral? This is the category we want to know about. And this is all the other techniques we are doing. We are trying to figure out about this category. So I'm chemically chiral if I can be transformed, if I cannot be transformed from one to its mirror image. So what does transform mean? So transform is going to mean we're going to be able to, the chemical structure of the molecule may be able to move parts around, right? So we might be able to move parts, but not the whole thing. So for example, we get these, I'm going to zoom in here. We get these little things here saying we can spin this piece. Just that little piece can spin. Okay, and it's like a propeller type of situation. So the chemical structure enables the molecule to change. So we can have that happen. So for instance, let's look, I have two examples where both of these are going to be achiral here. So for this molecule on the left, this is actually the Hoff link. So there's one component to the molecule here. All I'm going to do is I'm going to take that one piece and I'm going to turn it over. That's a rigid motion for that one piece. Since they're in two components, I can do rigid motions to each piece separately. This molecule is big enough to do that. Then I'm going to take this little chunk right here and I'm just going to spin it backwards to get this chunk. Okay, so I can do that. So these are going to be the same, but it's chemically achiral because of this motion right here. This propeller right here allows it to spin. It's not geometrically achiral because geometrically the whole thing is like one unit. Here's another example. If we had more time, I actually give 2 lectures only on this molecule itself. It's really interesting. But this is another one where you can spin it and things, and it'll be achiral as well. So again, last point here, just to hammer it home, pharmaceutical companies care about this one. We want to know what the molecule is doing chemically. But I'm a knot theorist, so I care about the third category, topologically chiral. So topologically chiral says I cannot be deformed to its mirror image. If the whole thing was fluid, I could stretch out bonds, I could whip it around, there's no rigidity, I can completely move it. So let's go back to this molecule here. So this one's going to be achiral because I could just take this piece, I can spin it around and put it over here. I can take this piece, spin it around and move it over here. I mean, molecules don't work that way, right? But if they could, I could do that. So this is called the Mobius ladder, synthesized around 1983, my birth year, actually. This was the first instance of using knot theory and topological methods to look at chirality of molecules. This was the first instance, was this one. And showing that this is topologically chiral is one of the hardest things in this area. If you're familiar, double branched covers, some Hegard splittings. I see Anthony's like, oh, okay, yeah. It's very difficult to show. So we're not going to show it, but we're going to claim it. So just put a little summary. What's really great is we have a relationship. So if I'm geometrically achiral, I am also chemically achiral, which means I am also topologically achiral. If I have rigid symmetries that I can go onto my mirror image, I'm all of them, right? We have a Venn diagram here. So that's really great. So if we care about this category, I meant to highlight that, right? We care about the chemically achiral. So one way to show chemically achiral is if I can show it's geometrically achiral, means I'm automatically chemically achiral. But we have the relationship the other way with chirality. I'll just put C's. So if I can show something as topologically chiral, I already know that it's chemically chiral and it's not the mirror images are not the same. So, right, what I skimmed over, hey, it's really hard to show something in this area topologically. So if I can't show things by, drug trials, experimentation, things like that, I can go to topological methods to figure out if my chemical I think so. That's me. I think all things knots are cool. Okay. So I want to do the next dives are the next topics are a little more shallow, go a little quicker, but I thought this was a cool one. Let's talk about protein folding. So this is an active area of research of mine that I started about 2 years ago. And I'll just say a couple brief words here. Proteins fold. They not. That's what we're going to look at. So the mechanisms of how that happens aren't fully known, except in December 2020, I had to write this down this morning, DeepMind used an AI to answer questions about why and how proteins fold. This research hasn't been published yet. It soon will be, but I do have the link to the article that I will show you. So some of these questions are now starting to be answered, which is really exciting. But at the time of writing this talk, we don't know. Oh, question. Are you familiar with or do you work with Protein at Home project? I don't know what that is. So I'll definitely look into that. I do want to point out the place I primarily go for things is going to be not prot. And that's where I get a lot of my data, which I have a link for you as well. Okay, proteins fold. 5 proteins or 5 knots have been discovered in the protein database that are seen in fold. So we get the trefoil knot and its mirror image. We get 4-1, the figure 8 knot. We get 1 view of the 5-2 knot and 1 view of the 6. Mirror. So a lot of times, how do we study these things? We look at experimentations, we create simulations. But for a mathematician such as myself, who's a theoretical mathematician, I look at theoretical models. So one known model is the following. Screen, there we go. And what the Flappin model says, okay, suppose I have an open protein chain. I'm just going to color it in 4 segments. So here I have to be a little bit more fluid with what I'm looking at. So proteins have certain configurations they have to stay in. There's distances that need to be preserved. So I'm going to look at templates. I'm just going to take it completely in the theoretical not sense, so I can move stuff around and change length just to look at the pictures. So I'm going to color in 4 segments. I'm going to twist up part of the red segment. I'm going to twist up part of the green segment. I can have 0, 1, or 2 twists. That's the first step. Second step is I'm just going to take this piece and elongate it over the black or under the black. And then I have 2 options. Top. My screen's a little slow to get the thing. It's coming. Or I can take the green loop like a jump rope through. Both result in figure 4, but both are distinct pathways. So they produce a different intermediate knot, but the model still gives the same knot at the end. And then to make it a mathematical knot, we just connect the ends. We don't really care because the knots hold shape due to thermodynamics in the protein. So what this model says is I get 8 possible configurations of what we look like. So since we're a little low on time, I'm not going to go into the nitty gritty, but the Flatbed model says, hey, I can make any protein knot using this method. It falls into one of these categories. And that is true. Their model encompasses every single knot that's been found and supports the probabilities of what knots there are. Some of these configurations are the same as others using Reidemeister moves. They also predict some other knots come up in this model that haven't been found in proteins, but maybe they could. These would be the likely candidates of ones that would show up. That's hypothesized. We don't have that data. I think that's cool. But what I think is cooler are virtual knots. So there's another type of knot called a virtual knot. So a virtual knot is take a normal knot and I'm going to add a third type of crossing. And I'm going to indicate it by this little circle. Okay, so this is a relatively newish idea in mathematics. It came about 1999 by Louis Kaufman. His paper came out on this. So a lot of good undergrad research questions involve virtual links and virtual knots because it's a newish area of mathematics. But what does this virtual crossing actually mean? So we can think about it in a number of different ways. So just like the levels of defining a knot, there are levels of defining this crossing. If I was talking to my family, I'm going to lie and say it's a self-intersection. It's not, but that's what I would tell my family. It's actually the way the knot is projected when you're looking at the knot on something called a handle body, and it interacts a certain way on the surface. We don't really care about that. That's a little technical. The working definition says it's an ambiguity. We don't know if it's over or under, so it's kind of both. Kind of like Schrodinger's cat. Is it alive or dead? Well, it's both, but like, how can it be both? That's kind of what we're going to view a virtual crossing as. Well, it's over and under, but like, how can you do that? So we can look at proteins as virtual knots, and this is how we're going to do it. So here I have a protein chain that's kind of folded, but I want to make it a closed structure. So how am I going to do that? Well, one way is to go underneath, right? One way is to go on top. Or what we're really going to say is we don't know because in nature it's just open. We're going to call that ambiguity a virtual crossing. Okay. And it makes a difference. For instance, this turns out to be the unknot, the other one turned out to be the trefoil knot. So when we do this, we can find that virtual knots occur in protein folding as well. And it's primarily these 5 small percentage of other ones, but they can't figure out which ones technically are because the knot tables for virtual knots aren't good. There was a lot of knots in that sentence, sorry. But what we should notice here is the virtual crossings in each of these that have been observed, only 1 or 2, right? There's not a lot of virtual crossings here, right? There's not 3, there's not 4, it's relatively low. So this is what I have my students working on. We are coming up with a model that not only produces the classical knots that have been found, but the virtual knots as well. So the way we're doing this is have to inside red could go over or under the black. So I'm going to call that a virtual crossing because there's ambiguity there. And then when I thread through the blue with the blue strand, like an eye of the needle through the other ones, we have a system to say any one of these can be virtual crossings. All 4 of them won't, because remember, 1 or 2 virtual crossings come up, but we have a system like, it's really quite ugly at the moment, but maybe we only consider this a virtual crossing or just this one. So we're looking at different routes of this flapping model to encompass those virtual links. So we have a couple of these models, but now the question, the real big question is, what knots do we get? We have to make sure we get those 5 classical knots. We have to make sure we get those 5 virtual knots. And how do we tell they're different? We went into this whole thing of like, how are they the same? Oh, I can just like bend it to get the other one, but how are knots different, right? This is an invariant discussion to have now. So I'm going to just give you a really brief look behind the curtain of some of the computations that I make my students do. We're not going to spend a lot of time on it, but I do want to show, just like I tell my parents, we do more than just like solve equations, we do other things. Just a look behind and see what I'm having my students do. So if you're familiar with knot theory at all, I'm going to be computing the Jones polynomial. If you're not familiar with that, I'm taking the knot, I'm making it a polynomial. So this is my obligatory technical slide. So the Jones polynomial is going to be, I actually have the rules for the bracket polynomial here. It's going to be a recursive formula to get a polynomial from a knot. There are certain rules. It's one, if I have the unknot and something else, I can change this are but what we're going to, I'll say it in words here. In your picture, pick whatever crossing you want. We're going to get rid of it. And we're going to do that till we have only virtual crossings left. How do we do that? I'm going to pick this crossing. I'm going to get rid of it. So I highlighted it here. So the first one, to get rid of it, I can now attach these ends together, which gives me my first option, or I can attach these 2 together to get rid of that crossing. There are 2 ways to get rid of it. So I'm just going to break that down into the 2 cases. That's precisely what this says is I'm going to take a crossing, we're going to get rid of it 2 ways. This is what happens to the polynomial. My polynomial is going to be in terms of A. Pick your favorite letter. It does not matter. Maybe not K. And then we're going to do that again and again and again. But now I'm going to do it on this knot and on this knot. So I picked this one. I'm going to take this crossing and I smooth it out again. It adds a horrible thing to my polynomial. And then notice this red piece turns into this red piece. So now I only have to continue on with this piece. So it's like I'm getting a triangle of breaking down my knot all the time, this like tree graph here. And then I continually look to get this polynomial in the terms A. I believe this specific one turns into a degree 17 polynomial. I don't know, but it keeps going and going and going. So this gets really complicated. So my students have like a database of knots and what their polynomials are. So hopefully we don't have to do this for every single knot. And then we try to find in the virtual knot table, does it have the same polynomial? If it does, I can use those Reidemeister moves to see if it's the same. Here come my cats, sorry, there's one. And if they're different, we know those are different knots. So that's currently where we are. This is active research. So they're doing a lot of these computations right now. I have about 4 minutes left. So I'm just going to do a super, super, super shallow dive into my last area. Luckily, this is the one this is the application most people talk about. This is the easiest to find online and other things. The DNA recombination events. This is when I first learned that knot theory was like more than just theoretical area. So our DNA is very long, it's flexible. We can have linear DNA. we can have circular DNA, and then we can have circular supercoiled, so super twisted DNA. So like circular DNA, mitochondrial DNA is circular, other things. Here's the classic image. If you go to Google, type in DNA knot, that's the one you're gonna get. So you can coat your DNA in like I believe it's like a Rec A protein, and then you take a microscopic image, and then you can kind of see where it goes a little hard, like that crossing's like this. I just put up some images, and you can expect your DNA to become knotted, right? It's really long in a very, very tiny space. So if you still had earbuds that had wires, right, they're really long, tiny space, they're always knotted, right? The percentage that it will be knotted, I think it's like a 90%, 94% chance it'll be knotted after a certain amount of time. So we can look at different aspects of knot theory with this. This is the one I'm going to focus on in my last 2 minutes. You have an enzyme ball, comes into your DNA, does something to the DNA, and then it leaves. And what knot theorists are being asked is what's happening inside that ball, because we can't see it. So what is the action is that enzyme's doing? I can see the before, and I can see the after, and I can see where it occurs, but what is happening on the inside? That's the question we want to know. So we want to create a model to answer that. So here's kind of the generic picture. We don't need to go through definitions here very much, but what's happening inside of the black ball? So these are the recombination events. So you get sites close together, they do stuff to each other, you get a new DNA strand. So I'm going to draw the picture instead. Okay, so should I draw the picture? Yes, this is what I'm going to do. Okay. You have a ball, and it's doing something else. So the before picture, maybe you have something where it just looks like this, and that's the before picture. But the after picture maybe looks something like this. So I'm giving away the secrets, right? I'm showing you what's happening inside the ball right now. But the question is, can we always figure out what this is? If you know the before and you know the after, can you always solve for the inside? Well, that's tricky. So a lot of it's going to be based on observation. So I will say that the main theorem is if you have the following. So we notice if there's no recombination event, sometimes they got the unknot. If there was two, we got the Hoff link, did it again, we got another link, did it again, we got another link, did it again. Can we know what the enzyme action is? And the answer is yes. You can figure this out. It is very difficult to prove. So this is observation. This is the theorem. Right. So without going into details, proving a theorem, right? Math fact, right? Proving that, it's really, really hard. So this uses, again, for Anthony, double folded branch covers, Heegard splittings, and a little bit of homology in there as well. But concretely, it can be shown that this is always the case with this specific protein. So you can do this with other proteins or not. I know that was super quick towards the end there, but we're kind of out of time. So I'll let it slide there. I do want to say in the first link of the chat, there's a link to this web page, which has links to all sorts of different application, not websites, programs that you can draw knots with, protein databases that you can play around with the proteins and see what knots are folded in there and things like that. And I'll be continually adding to that as well. So thank you for your time and your attention, especially on a Friday. I really appreciate it. So